This is AnalogGPT. It's made up of 53 pages filled with tables of weights and biases. I used a basic transformer architecture built completely from scratch and trained on the Wikitext2 dataset. The model size is just 15K parameters, which is extremely small compared to modern language models. That means its predictions aren't always great. Actually, it's very poor. But it's perfect for understanding how transformers work. At its core, GPT, short for Generative Pre-trained Transformer, is just math, a giant array of numbers. If you've heard of a paper, Attention is All You Need, that's the one that introduced the transformer architecture, GPT is a stack of decoder layers introduced from the paper. With some calculations, you can predict the next token. In early days, transformer models weren't even designed for questioning and answering. Their main goal was simply predicting the next token. At first, the model is randomly initialized. But through training, say using a dataset like Wikipedia, the model starts learning patterns. For example, it might learn that after the word Shawshank, the word redemption is highly likely to follow. It learns this by adjusting its weights and biases as it sees more examples. So, in theory, you can predict the next token with just paper, pen, and a lot of patience, as long as you have every weights and biases. That's exactly what AnalogGPT is. Before diving into how to use this model, I have one disclaimer. All the source code is on my GitHub, the link is in the description below. You can download the full PDF and try it by yourself. If you like this idea, please subscribe and drop a star on my GitHub. To use AnalogGPT, start by writing the prompt on your paper. For example, let's say you want to predict the next token of the cat is. Now, use the tokenizer table to tokenize the input. We got 70, 216, 18, and 25 in this case. First, use the token embedding table to convert each token into its corresponding embedding vector. If your sequence has 4 tokens, this will give you a 4 by 12 matrix, 4 tokens each represented by a 12-dimensional vector. Here, 12 is the embedding size of the model, which is a tunable hyperparameter. Increasing the embedding size allows the model to capture more complex patterns and improves its representational capacity. Once you have the token embeddings, apply layer normalization. As described in the original paper, layer normalization adjusts each embeddings so that it has a mean of 0 and a standard deviation of 1. Next, compute the query key and value matrices. Since the math can be a bit complex, I've pre-calculated the results to 3 decimal places for this example. After getting Q, K, and V, compute the attention scores by multiplying Q and K transposed. This gives you what's called the QK score. You can visualize this with a heat map to see which token the model is attending to. Then, multiply attention scores with the V values and compute the final attention output. Add the original input X to this result. This step is known as a residual connection. After that, apply layer normalization again and pass the result through the first multi-layer perceptron layer, MLP for short. Apply the Jello activation function, then pass it through the second MLP layer. Add another residual connection at the end of this step. This whole process, attention, layer normalization, MLP with Jello, second MLP, and residual connection again, is repeated 4 times in total. After the final layer, you get an output called xFinal. From xFinal, take the last token's embedding and use it to compute the final logits using the output weights and biases. Then, pass those logits through a softmax function to get a probability distribution over the vocabulary. Finally, select the token with the highest probability, and that gives you a predicted next token, all. Yes, it's a lot of computation, but technically, you could go through all of this without a GPU, just with your bare hands and some patience. So, the main question is this. Once some models, weights, and biases are fixed after training, Running an exact same prompt in inference mode should always produce the same output. Yet ChatGPT and Claude often produce different answers to the same prompt. How is this possible? During inference, models employ techniques like temperature scaling, top case sampling, and nucleus sampling. Temperature scaling adjusts the logits. Values above 1 flatten the distribution and increase diversity. Top K sampling randomly selects from the K most likely tokens, while nucleus sampling, known as top P sampling, dynamically expands the candidate pool until its cumulative probability exceeds a threshold. This controlled randomness is why the outputs can vary. Today, we explored AnalogGPT and walked through how the transformer architecture works from the ground up. Thank you for watching.